start the M4V now, and we'll carry on. I don't quite know how long it is. 40? 36, okay. Right, so let me introduce Peter Stevens.
Wow, great to be here.
Oh yes, it's Peter Stevens from Stony Brook, and he's going to be introducing the Rietveld method.
Which I think we should say that Peter, originally we had indexing in the schedule before Rietveld. Peter felt very strongly that it should be flipped around. He felt that the indexing really wouldn't make an awful lot of sense without the Rietveld. So
right.
that explains the sequence.
Hello, I'm Peter Stevens. It's my pleasure to give 2 tutorial talks on Rietveld refinement and lattice indexing today. I'm sorry I can't be with you right now, but I'll be there in a few days. I sure hope the technology of these video recorded lectures works out. I want to start this talk by going back in time to 1995. 1995 is halfway between my first scientific publication and the present date, and so it marks the midpoint of my scientific career so far. But it's specifically important to me, and to this field of powder diffraction, because it was the year of a conference on structure determination from powder diffraction data organized at Rutherford Lab and Oxford University by Bill David and Kenneth Shankland. At the time, I had learned quite a bit about high-resolution powder diffraction from some experiments in icosahedral quasicrystals and fullerene materials that I had done. But it was at that conference that I saw the breadth of problems that were naturally matched to powder diffraction. It was there that I learned about many of the techniques that had been developed and that were being developed at the time. And it was there that I met a number of wonderful new friends and scientific collaborators that I continue to value. In retrospect, that meeting really was a turning point in my own scientific career. Finally, to the best of my recollection, 1995 is the first time I saw a seminar or conference talk presented with PowerPoint. Kenneth Shankland gave a bravura discussion of the use of maximum entropy phasing methods, and was somewhat annoyed when the audience had more questions about the technology of PowerPoint than about the topic of his talk. So it's with that in mind, I hope that this video presentation works out. Since Rietveld refinement is the last step generally in the analysis of a powder diffraction pattern, why is it so early in the program of this school? I'm sometimes asked, can you help us use Rietveld refinement to solve a particular structure? Or you'll read in a publication, the structure was determined by Rietveld refinement of so-and-so data. Well, it's the last in a series of steps, but it's generally the only one which is available for public inspection, so maybe it's not surprising that people think that it's most of what we do. And after all, you judge a restaurant by what comes to the table. It depends on all the prior steps of preparation, even if you don't see them. So I want to start with a few disclaimers and thank yous before we move on to the real content of this talk. First, I'm going to be showing data from my lab and my own publications. I certainly don't believe that they're the most interesting or informative, but I do want to show you what happens in the kitchen before the dish is presented, and I really don't know that about anybody else's work. I'm going to be showing you refinements based on the use of the Rietveld software Topaz and Topaz Academic. You'll see plenty of other software which has very much the same power and utility in other talks in this school. I want to express my appreciation to collaborators who've brought a lot of interesting problems my direction. I'll mention them in turn as we go along. I want to express my great appreciation to the people who have written software documentation and tutorial information and made it publicly available. The community has benefited enormously from this, and I hope you'll join me in thanking those people. And finally, I have a lot of appreciation to all of the people here at this workshop and elsewhere who have advanced the state of the art simply by practicing it. I think it's worth looking at what came before Rietveld refinement in terms of structure determination from powder diffraction data. Here's a little tidbit from 1948, the crystal structure of plutonium sesquicarbide, worked out by W.H. Zachariasen. Don't worry, I'm not showing you anything you shouldn't see. This was taken on a Debye Scherer camera with film and based on the observed peaks and absences, the space group was inferred. You can see that the data is quantified in terms of peak intensities that go from very weak to very strong. But nonetheless, this is enough quantitative information to come up with a structure solution based on the space group. There really is one plausible place to put the plutonium atom to get the density right. And that's in a special position, XXX, and so only the parameter X needs to be determined. And here you see some steps that Zachariasen went through to match calculated and observed intensities for various choices of the parameter X. 0.05 works out well, and so that's the structure that we see here. The presence and the likely position of the carbon was inferred. So then along came Rietveld with the absolutely radical idea in 1969 to look at all of your data, the entire profile. Basically, the suggestion is to compute a model diffraction pattern based on the crystal structure and parametrized profile functions and to adjust structural and line shape parameters to get the best agreement. Here is a picture of Rietveld's computer, or one like it. According to the paper, Rietveld's computer actually had magnetic tape units, which of course were required to be able to hold the large amount of data that goes into a Rietveld computation. The Rietveld method was first applied to neutron powder diffraction data from a constant wavelength reactor source. A method to unscramble overlapping peaks was really needed for such data sets because the resolution of such an instrument is relatively poor, but also the use of CW neutron data provides the opportunity for Rietveld refinement to work in its earliest incarnations because it's possible to model the line shapes, the diffraction peak shapes, accurately. So what goes into a powder diffraction pattern? Well, it's a series of elementary recipes. If you know the crystal structure, from the unit cell you can compute the reciprocal lattice, the space group. That tells you where the diffraction peaks are in 3 dimensions. Now we have to collapse those into 1 dimension for a powder diffraction pattern. At the same time, the contents of the unit cell, the atoms, allow you to calculate the intensity of each Bragg reflection. And so that Bragg reflection, that should be the intensity of each of the peaks that's marked with a tick marker here. Both the instrument and the physical sample affect peak shapes in various ways that we'll be talking about soon. And there are other factors that might go into it, such as a background function, preferred orientation. From all of that, you can compute a powder diffraction pattern, which is a straightforward task if you know the crystallographic information and if you know about your diffractometer instrument function. We go the other way. If you have a powder diffraction pattern, what information is in it? Well, the peak positions are determined by the lattice and space group. The peak shapes are determined by both the sample microstructure and diffractometer geometry, and the peak intensities are determined by placement of atoms within the unit cell. Here's an example of a pattern of an organic molecule. This is a drug that was under development, and you can see that the first few peaks stand distinct, but if we zoom up to a higher angle part of the spectrum, here in this 1 degree range, there are 21 different peaks contributing. The peak positions are determined through elementary crystallography. You can look up these equations anytime you need them, and they basically tell you the angle. I'm talking about constant wavelength diffraction now. They tell you the angle where you will observe a peak of the given HKL, where these parameters A through F depend upon the metric parameters of the unit cell. We normally think of diffraction peak shapes as being a convolution of the intrinsic and the instrument. And, well, here is the constant wavelength neutron diffractometer. The peak shape function was originally written down by Caglioti, Pauletti, and Ricci some time ago, and what they found was that if you convolute together the contributions of a mosaic monochromator and all the collimators, you end up with a peak which is approximately Gaussian, very nearly Gaussian, that has a width that's this polynomial, and they provided closed form expressions for the parameters u, v, and w. In Rietveld's original paper, he measured peak widths versus 2 theta and compared them with that prediction. There are data points here that fit on the curve that was computed just based on the geometric parameters of the diffractometer, and the fit is very good. Here are sketches of 3 typical configurations for laboratory diffractometers. Probably the most familiar is the Bragg-Brentano diffractometer. This gives a nice trade-off of intensity versus resolution, but it turns out to have a rather difficult line shape to understand in detail, but you'll be hearing more about that later on in the course. The other way to diffract neutrons from a sample is from a spallation source, and there's a rather complicated model of the pattern and the time structure of the pulse that comes out of such a thing, but it can be modeled and is very powerfully used in Rietveld analysis. Synchrotron radiation is a very attractive source of X-rays for powder diffraction. The upper picture here shows the beamline at X16C at the National Synchrotron Light Source, the one that I used for most of the data that I'm going to be showing here. The beam coming in and striking the sample is essentially parallel because it's coming from a very small source some 15 meters away. This beamline has the additional feature that the outgoing radiation is not collimated through a slit, but rather is diffracted by another analyzer crystal. So this instrument really does measure angles. Only an X-ray that diffracts from the analyzer crystal is going to find its way into the scintillation detector. One can improve the optics of such an instrument even more by using a collimating and a refocusing mirror. The optics of this have been considered in detail by Fabio Gozzo and company, and I'm sure that you're going to hear about that later in this school. So let's not say any more about the instrument contributions to the line shape. Let's look at the intrinsic contributions from the sample itself. First of all, let's think about grain size. Suppose you have a spherical grain of a crystal that's a simple cubic lattice. Here's a numerical computation for a grain that has a diameter of about 100 lattice parameters, so 500,000 atoms inside of it. And you can calculate the powder diffraction peak shape directly from the Debye formula by summing over pairs of atoms. And here's the numerical result for that in black, in both a linear vertical and a logarithmic vertical scale. You see that empirically the function needs tails. It tapers off more broadly than a Gaussian function does, but not as rapidly as a Lorentzian. And so there are various schemes in practice that are used to get an approximation to the correct line shape. Besides the shape, there's of course the width itself. In 1918, Scherer wrote down a formula that relates the size of the diffracting domain to a shape factor, wavelength, the width of a diffraction peak in 2 theta, and this shape factor depends upon the shape of the particle. So from this number, from the numerical computation, we see that the shape factor must be about 1.1 for a spherical particle. Of course, a distribution of grain sizes, instrument resolution, things like that will wash out the observed peak shape function. There is very detailed information that can be recovered from diffraction profiles. Again, that's a topic for lectures later in this school, but I'm not going to consider it further here. Another contribution from the sample to the diffraction peak line shape is due to strain broadening. This generally arises from elastic strain within the grains caused by lattice defects, but it's often okay to pretend that there's a narrow distribution of lattice parameters. So here's a diffraction pattern along the horizontal axis, and if we imagine that the red crystal here has a slightly larger lattice parameter than the violet crystal, you can see that successive orders of diffraction are going to have broader and broader diffraction peaks. That leads to a width of the diffraction peak in 2 theta that's proportional to the tangent of the angle, theta. So if we put all of these things together, both the instrument and possible sample contributions, if we imagine that there could be a Gaussian contribution or a Lorentzian contribution, you can wind up with a line shape that has an awful lot of parameters, and this will take account of both the instrument and the sample in one set of parameters. These parameters might be determined empirically by using a standard sample and then refining them to fit your own particular sample. The third thing that goes into the diffraction pattern is, of course, the set of intensities. Given the atom positions in the unit cell, the integrated intensity of a given reflection, HKL, is given by this formula. Here's the Debye-Waller factor. Depending upon polarization and the exact sample geometry, this Lorentz polarization factor might be different, but it's elementary to put in the right one. Of course, the atom positions here come from space group operations on independently defined atoms in the irreducible cell. So in a Rietveld refinement, we'll probably be comparing the observed data points y-obs, each of which is associated with a standard uncertainty, against a model which is made up of a large number of different pieces: the atomic positions of the atoms, lattice parameters, whatever line shape parameters are being used to describe the shape of the observed diffraction lines, both instrumental and intrinsic contributions. There are some other factors, for example, an axial divergence correction to the line shape that I'm not going to really take the time to describe now. Background, there's frequently a background observed. It's usually described as some smooth function of 2 theta, and there can be other effects that we're going to try to correct for in the data, such as an offset of the detector arm from 0 angle, preferred orientation in the sample, and so on. So all of those go into building up a calculated line shape as a function of 2 theta. These are usually measured in a step scan, and so I'm going to write these as sums. And we're going to define several figures of merit. Here's the weighted profile factor, and that measures how well the observed data matches the calculated model. There's an expected R factor, which tells you basically how good a fit of the weighted profile R factor you could expect to get. And there's the familiar chi-squared. In Rietveld refinement circles, one usually refers to a goodness of fit, which would be the square root of chi-squared. And you can see that if the difference between the observed and calculated intensities at each point are on the order of the standard uncertainty, all of the terms in this sum are going to be on the order of unity, and so the goodness of fit ought to converge to something like unity because there are m points in the data set. And that's in fact what let us define the expected R factor as how low we think the R factor ought to be able to get down to. I would say typically experimental data might have an expected R factor in the range of a few percent, 3 to 5 perhaps, and a typical good refinement might have a goodness of fit that's somewhere in the range of 2 to 10. An unfortunate fact about powder diffraction, at least relative to single crystal diffraction experiments, is that there is not a clear threshold for R factors or goodness of fit that enables you to distinguish a correct from an incorrect solution. The Rietveld method also gives you a way to measure or to estimate from the data alone the integrated intensity of each peak. If you have data that looks like this, and let's imagine that this blue curve is the Rietveld fit at any particular point of calculation, well, it's easy to see what the experimentally measured intensity of this peak, which stands alone, is. It's just the area under this curve that you could measure if you had a marker that writes. It's just that area under that curve is all assigned to that peak. If you have overlapping peaks, how do you divide the intensity of any given point, whether this should go with the orange peak or the greenish peak? And the Rietveld assignment for that is to divide its intensity according to the proportion of each peak at that point. So intensity here is going to be assigned as belonging more to the green peak than the orange one, whereas intensity here, the measured intensity here, is going to be ascribed almost completely to the orange peak and not the greenish peak. So that gives you a way to estimate the intensities of the peaks that are partially resolved. Of course, it's dependent upon the model, the Rietveld model, at any given stage of iteration. Let me illustrate the same idea with equations. After a Rietveld refinement has converged, the calculated model at a given angle 2 theta is going to be made up of the background function at that angle plus the sum of whatever peak shapes provide intensity at that 2 theta times their respective intensities calculated from the crystallographic fit. Now, if we define the observed intensity of a particular peak to be the integral, the sum over all 2 thetas of the observed intensity minus background, and at any 2 theta where there may be more than one peak appearing, we're going to just apportion that intensity according to the fraction of all peaks that contribute, that is the peak that we're interested in. So that apportions the intensity according, in some rational way, according to the Rietveld fit. There's of course a bias in there, and it allows the calculation of a Bragg R factor, much the same as is used in conventional single crystal crystallography. And that suggests a rather clever method to extract intensities from a powder diffraction pattern and also to see what's the best you're going to be able to do. Let's go through the Rietveld procedure. We're going to start with all calculated intensities at unity, and we'll do repeated Rietveld refinement cycles without any atomic structure. In each cycle, we'll replace the calculated intensities with the so-called observed intensities determined by that same procedure. At the same time, you can refine other parameters like the lattice parameters, line shape, background. That's going to converge to the best possible fit to the experimental data within the parameters of the model that you're using. And it'll also provide a good estimate of the set of diffraction peak intensities. You might be able to use that in some sort of structure solution step. The best thing is, perhaps, that any Rietveld program can be readily modified to perform a Labai fit in that way. Let me illustrate the process with some data that we're going to be looking at some more soon. This is a pattern of rubidium 3C60. Let me zoom in here on just a few peaks so you can see what we're doing. Here's the raw data. So I set up a Labai fit control with 0 iterations. So we're just going to see where the Labai process starts from. What have we got? Here's the difference curve on the bottom. This black trace is the data, and the red trace is a model. And right now the model is a series of peaks at the face-centered cubic lattice. I actually made kind of a wrong guess of the lattice parameter. You can see that the peaks don't exactly line up. And of course the intensities are ridiculous. So now let's switch this and do one cycle of iteration. So it's going to adjust lattice parameters, backgrounds, other things like that. And it's going to readjust all of the intensities according to the Labai method. Click, and that's gotten a lot better, hasn't it? What have we got? Well, the intensities are more reasonable, and it looks like it adjusted the lattice parameter a little bit. We could do better. And so let me just keep doing one cycle at a time. You see each time we do another cycle, it's iterating closer to a correct solution. Let me just go in and revise this file so that we can do some reasonable amount of iterations. Instead of one at a time, let's do 10 cycles at a time. Back to Topaz Academic. So here come 10 cycles. Boom, boom, boom. And you can see that if we do that very many more times, we'll have a pretty good fit for the whole pattern. So that's how the Labai intensity extraction method works. There's another technique for obtaining a computed fit to an experimental powder pattern due to Pauli. This is also a Rietveld-like procedure in which a calculated line shape is compared against the data. In this case, there is an additional least squares parameter for the intensity of each peak in the pattern. That's obviously a lot more peaks, but contemporary computers can easily invert large sparse matrices. An ordinary least squares fit will be unstable if peaks closely overlap. The the matrix is guaranteed to be singular in the case of exact overlaps, for example, 333 and 511 cubic peaks, but there are numerical ways around that problem. I'm not going to talk about them here. The nice thing about the Pauli fit is that it provides a covariance matrix, which comes from the least squares refinement of all of those individual intensity parameters, and that essentially measures how strongly correlated each pair of reflections is. That'll be unity in the case of two reflections that exactly coincide. And then once you have that covariance matrix, you can do a structural refinement based on just the set of extracted intensities with the covariance matrix, the inverse, built in. This has been proved to be equivalent to a Rietveld refinement of the entire structure by Bill David in this very interesting and apparently little-known paper. So let's demonstrate some of this by going through the structure solution of rubidium 3-carbon-60. This is an interesting material. The structure has been known for some time, but there's quite a lot to be learned by going through it in a Rietveld refinement. So this is some rather old data connected to the National Synchrotron Light Source. I'm going to be going through the steps of refinement done in Topaz Academic. You'll learn more about Topaz Academic as the workshop goes along. I'm just using this as a convenient tool rather than trying to teach you the details of this program. So we start out by looking at the data, and more or less by inspection I can tell that this is face-centered cubic. This characteristic alternating pattern of 2 peaks, 1 peak, 2 peaks, 1 peak suggests face-centered cubic because of the reflection conditions. We already did the Labai fit as a demonstration of this, but let's look at the results from that. What we have here is the black line. It's hard to tell them apart in this fit, but there's a kind of a noisy black line that's the data. There's a red line that's a fit, and the all-important difference curve is down below here. So it's a good start, but we can pretty quickly see some problems in it. Let me zoom in on a region here around just these few peaks. And now you can see that the red curve, which is the calculated model, is sharper than the data for this peak, which is what? That's the 062, not very far away in angle at the 444. You see that the data is sharper than the model curve. You can see that especially clearly in the difference curve, which looks like the second derivative of the peak shape. So that's a kind of a flaw in the computation of the model that I think we want to deal with before we go any further. Here are the numerical results of that fit. The size broadening parameters turn out to be very small. We can deal with this problem of the width not monotonic in diffraction angle on the basis of a model of random isotropic internal stress leading to a dependence of strain on the Miller indices, or a more phenomenological approach. Either way gives you the same equation. And it's just a few lines to write that into the Topaz script. The wonderful thing about Topaz as a research tool is that if you have an idea that nobody's ever put into an available Rietveld program before, implementing it is just as easy as writing an equation into the script and seeing how it works on your data. So here's the fit we had before. I put that new script in, and well, that seems to have helped. Let's look at the entire fit. Yes, that's much better. There still are some little issues here, but I think we've reached the point of diminishing returns, trying to deal with those. That did give an improved fit. Our factor went from 5.3 to 3.6%, and it's plausible that not dealing with that would have produced a systematic error on intensities in refinement. So let's go ahead now and try to actually solve the structure. We're going to regard, as a first look, we're going to regard a carbon-60 molecule as a big sphere, and a face-centered cubic packing of those spheres leaves one octahedral and two tetrahedral vacancies, cavities per sphere, and those are fairly natural locations for the rubidium ions, so that's a good hypothesized starting point for them. So an ordinary soccer ball has 1, 2, 3 mutually perpendicular twofold axes, and if you let those point in the directions of the edges of a cube, then the body diagonal of the cube naturally makes the threefold axis that comes through the hexagon of the soccer ball. And then if you look at the nodes, there are 60 in all, and in M3 bar symmetry, you need to enumerate separately 1, 2, 3. The first one is on a coordinate plane, and the other two are in general positions. According to that hypothesis, which remains to be tested, there are 3 independent carbon atoms, and we have to figure out what their coordinates are. The easiest thing to do is to make a random guess and refine their positions. So here's topaz, here's the poly fit that we're starting with. Here's topaz, and I've put in another script that's going to do that. Here's topaz in kind of a shake and quench mode. It's restarting with new random parameters each time that it converges. Here's a kind of a graph of the record of its successes and failures. I don't want you to think that we originally solved this problem in such a direct path. Knowing the correct answer in advance makes it much easier to find, and there weren't such powerful tools or such a good sample available in 1990. Well, let's stop this and look at the best solution, the best fit. And again, it's encouraging that we're on some kind of a right track, but it's very clearly unfinished. Also, if we look at this solution, that's a pretty ugly buckyball. You would expect fairly regular hexagons and pentagons around the surface of it, and if you just look at these bond angles, 109 degrees in a hexagon, 131 degrees across a pentagon, that seems very wrong. The next thing I want to try is based on the observation that in this FCC lattice, these octahedrally coordinated rubidions might be rattling around in pretty big cavities. Normally, the thermal parameter of atoms, at least in early stages of a structure solution, don't matter. But I'm going to try a similar search with different thermal parameters for each atom. So here we are back in topaz, now with a script that refines a separate isotropic thermal parameter for each atom in the cell. And let's let that cook for a little while, see what we get. We'll have a look at the best of those. And that's now a much better fit. You see that in fact it converged to a very much larger thermal parameter for the rubidium, for the octahedral rubidium site, but it's still an ugly buckyball. Well, that would be very exciting if we happen to discover that the charged fullerene was quite distorted relative to the uncharged one, but it would also be quite embarrassing if it turned out to be wrong. There are still some problems to be resolved. Also, notice that while it's a better fit than we had before, it's still significantly worse than the poly, and we're using the same line shape parameters that went into that poly. So there's still structural issues here. The next step in refining this structure is actually to go all the way back to the original choice of the space group. Notice that there are 2 possible orientations for the fullerene in this cubic environment. Could they be disordered? If we go to a higher space group, FM3 bar M, which consists of adding a second set of mirrors in 110 planes, well, that doubles the occupancy, the multiplicity, I should say, of each of the positions of carbon atoms. And of course, if you're going to have a disordered fullerene, you imagine that there's a 50% occupancy, a 50% probability of occupancy in one position or the other. So let's see how that works. So now we're going to do another refinement, starting with the same parameters, the line shape from the polyfit, but now changing the space group. And what we find when we do that is that we've got a very much more regularly shaped buckyball. Here's one of the hexagon angles is 122 degrees, one of the pentagons is 103. That's much more reasonable. So we're imagining that as you view this along a 100 direction, half of the time you're looking at a buckyball that's oriented this way, half of the time this way. And that produces really a very much better refinement. Here are plots of the refinements of this FM3 bar M fit, as well as the FM3 bar that we were working on for a while, and the poly. And you see that some of the problems in the refinement up to this stage, here, must be line shape issues not properly accounted for because they're also present in the poly. Well, we haven't solved everything. With an R factor of 4% rather than 3.61%, we still have a little ways to go. Realistically, Rietveld refinements never get all the way down to the quality of the poly case, and this is frankly quite a bit closer than one normally sees. There are some defects still that are crystallographic. Here's a problem that's not in the poly. Here's a problem that's not in the poly. So we've done quite a bit better than the defects that are in FM3 bar. What would I try next? I suppose the next thing to try might be anisotropic thermal parameters for the carbon atoms, but I think we've carried this far enough. It's drawing close to your lunchtime. Let's look at one more example. Here is this is paramethyl chalcone, and it's a member of a family of compounds that has a tremendous number of polymorphs, basically depending upon where you stick this methyl group. In this particular case, there's one form that's only available as a powder. It was initially indexed to an orthorhombic lattice with these dimensions, but there's a problem there. Paramethyl chalcone molecule has 17 non-hydrogen atoms, and as a good rule of thumb, organic materials have about 17 cubic angstroms per non-hydrogen atom. So if there are 300 cubic angstroms per molecule, into that volume you'd think there could be 6 molecules in the unit cell. There's no evident symmetry for mirrors or twofold axes. How are you going to accommodate 6 molecules into an orthorhombic cell? You can reject various possibilities until you come up with the idea that maybe the lattice is monoclinic with a beta angle close to 90 degrees. So a likely guess would be a space group of P21 with Z prime equals 3. Of course, as always, subject to confirmation, raises the question of which is the unique axis. So we ran dash several times with this data, and the best solution we found is the long axis is the 2-1 axis. In subsequent refinement, it turns out to be 90.05 degrees, not very far from 90 degrees, but the best solution from dash doesn't turn into a usable refinement. Here's a sort of a snapshot of trying to refine that structure, and you see some very strange angles and distances and atoms approaching too close to each other for sensible bonding. So that was a sort of a trouble. An interesting thing you can do in Rietveld refinements with molecules, conventional Rietveld would treat the atoms independently and refine the fractional coordinates. There are ways to define restraints of bond distances or angles, and you might even be, and you can, in all Rietveld programs, define rigid groups of several atoms which move together. Another approach that's built into Topaz is the Z matrix, where you build a group of atoms on kind of a scaffold of the previous ones. So here's a piece of the script in Topaz that defines a molecular unit by internal geometry. For example, this group of atoms is defined to be a regular hexagon, and there's a parameter that can be refined, which is just the torsion angle about this bond, which would rotate this aromatic ring relative to the rest of the molecule. It's a convenient way to refine structures, especially that are molecules. So when we look at the best solution that didn't turn into a usable refinement, by doing that kind of a Z matrix refinement, the resolution of this was, again, eventually we figured out, that if you take this molecule and flip it about either the vertical or this horizontal axis, you get a molecule that fits almost exactly into the same space. So it's possible that you can do that with each of the 3 independent molecules. There are going to be something like 64 metastable minima for a simulated annealing algorithm to get stuck. So we did a systematic search. We did Rietveld refinements for each of 64 independent starting points. And if you look at this histogram of refined R values and the population thereof, you see one very clear best solution. Here are a couple of pictures of the solutions. Here's a good one. Here's a not so good one. If you go in and look closely, some of these angles and distances are a bit funny once they've been refined, but you can especially see the difference in the quality of the data, the quality of the Rietveld fit. Now here's the data of that paramethyl chalcone, and let's run a refinement. First I'm going to run a refinement of what we decided was the correct solution that had the best R factor. And here it is. Well, if that's the best solution, what's with these big peaks that are seen in the difference curve? I'll tell you that the fact that all these peaks are positive, let's zoom in and look at a small region here. And now I can see that this is not just a matter of getting the wrong intensities. These are peaks that are showing up in places where there's no allowed peak for the lattice. You also notice that those peaks are sharper. They have a different shape. They're sharper than the actual paramethyl chalcone phase that's the majority phase. So I'm inclined to believe that there's just some crystalline impurity in here. If we look at the whole fit, those peaks continue to go, but let's now look at a higher angle region. And I think you can see that except for the spurious impurity phase peaks, the agreement between model and data, the red line and the noisy black line here, is quite good. There's really no structure in the difference curve. So that's a very believable fit. Let's just have a look at the not so good solution and see how that stacks up in comparison. Keep an eye on the difference curve here when I now run the one of the 63 incorrect solutions, and look how much more structure there is there. And if you zoom in on a small region of that, let's just look here, you see that there's really very little correlation between the calculated and the experimental data. So that really does reinforce my opinion that the correct solution is correct and this one isn't. Coming down the home stretch now, I just want to say a few more things about Rietveld fits. One of them is that when you look at a published Rietveld fit, really it looks like noise after the first few peaks. A lot of people would be inclined to look at this and say, well, these first few peaks match up very nicely, I bet it's right. But there's a tremendous amount of information here, and it's a mistake not to pay attention to it. Let's zoom in on a little piece of it here. Just that limited angular range between about 22 and 25 degrees. So here's a blow-up of that, and you can see that while there's statistical noise in the data, but the model really does fit the data very well. This is a fairly complicated structure of a magnesium borohydride with, oh gosh, 5 independent molecules in the unit cell. There's a huge amount of information in a good powder diffraction pattern and in a good fit to that pattern. And this leads me to something that I really want you to do anytime that you're working with Rietveld fits. It's very important to examine the fitted pattern carefully, more carefully than you can do with a little postage stamp picture that goes into most publications. Whether you're the author or the reviewer, I think it's really important that numerical data from Rietveld refinements must be deposited so that they can be examined by anybody who's interested. Another point I want to make is that the examples I've shown so far have been really good fits of really nice data. Make no mistake, these are exceptional. I think it's important always to bear in mind with powder diffraction data, you play the hand you're dealt. You're trying to get scientific information out of a sample, which, well, sometimes it's better than it is other times. You should get the science you can get and just see what comes along in the next deal. So I have a couple of illustrations of that. For example, we spent quite a bit of time on rubidium 3C60. That's isostructural with potassium 3C60. Here's the Rietveld fit that was originally published with that solution 20 years ago. And anybody would have to agree that it looks very poor by contemporary standards. Part of the problem is that the sample was in a heavy glass tube. We didn't really have an optimized synchrotron beamline to collect that data, so the intensity was much smaller. The software, ProfPV, old-timers here recognize that? It was much cruder than anything that we have available. But I'm not embarrassed about this fit. This fit really did suit the scientific requirements of the time. And I think anytime that you do a refinement, anytime that you're looking with powder data, anytime that you're looking with scientific data at all, you have to judge it according to that criterion. Does it address the scientific question that you're interested in? Last example. Here's a pretty bad powder diffraction pattern that we took recently. This is at 0.7 angstroms, so the maximum 2 theta of 30 degrees is a d-spacing of about 1.35 angstroms, but there really does not seem to be a lot of peak shape information up to there. You might actually be doubtful if you could index this pattern, and I'm going to leave it to Saul Lapidus to tell you the details if you care to hear them. But he did solve this structure, and here's a refinement of it. There really is nothing to complain about that, and I think it shows that even in what looks like broad blobby peaks, there's information to be dug out. Look at the number of peak markers that are present in the diffraction pattern of this material. Well, here's the structure that Saul Lapidus coaxed out of that data, and I'll leave you with a couple of questions to think about. Of course, the people who gave us that sample told us what they thought was in it, which turned out to be pretty much correct. They didn't know the exact chain structure, but they had the basic building blocks together. So I'll ask you, do you suppose the powder X-ray data is enough by itself to judge if this structure is correct, if you don't know anything about the alleged chemistry? Put it a different way, could the structure be incorrect in any significant way? And whatever your opinion on either of those is the outcome of sufficient scientific value to publish? I'm going to conclude here by saying that most of the work I've shown has been done by my students, Ashvia Huck, Jay Hyuk-Her, Kevin Stone, and Saul Lapidus. We also certainly appreciate the contribution of numerous collaborators who fed us interesting problems over the years. I could keep on going, but I think we're about due for lunch, so I'm just going to say, like this talk, no Rietveld refinement is ever truly finished, merely abandoned. Thank you for your interest.
Well, that's time to perfection for two reasons. One is that there will be no opportunity for questions, I'm afraid. We're right on the time of lunch. Peter will be here at the beginning of next week, as he said at the beginning of his talk, and so there'll be an opportunity to ask him questions then. Annalisa has something to say, but just to remind you to be back here at 2:30 in the afternoon. If you could be here 5 minutes early, that would be excellent.